Let us now address the problem introduced in the previous lesson: how to determine an expression corresponding to a given function. To proceed, we must first introduce some definitions. First of all, we define a literal as a variable and value pair. The pair x and 1 is denoted simply as x and represents the variable in its positive or uncomplemented form, while the pair x and 0 is denoted as not x and represents the variable in its complemented or negated form. More intuitively, a literal is just a variable as it appears in an expression, either in its positive or negated form. So, if the literal x is equal to 1, then the variable x is also equal to 1, and vice versa. If the literal not x is equal to 1, then the variable x is equal to 0, and vice versa. We now define a product term as a logical product of literals, and a sum of products as an expression formed by the logical sum of multiple product terms. Dually, we define a sum term as the logical sum of literals, and a product of sums as an expression formed by the logical product of multiple sum terms. One key characteristic of these expression forms is that negation is applied only to individual variables, which are thus referred to as literals. A product term in which the literals corresponding to all the variables of the function appear, and for which the function evaluates to 1, is called a minterm of the function. Specifically, in the product term, each variable appears in its positive form, x, if it takes the value 1 in the corresponding input configuration of the truth table, and in its negated form, not x, if it takes the value 0. Let me show an example. The fifth row of the truth table corresponds to an output value of 1. We construct the minterm by taking a in its positive form, since the first column contains a 1, and b and c in their complemented forms, since the next two columns contain zeros. A second example, a and b and not c, which is the minterm corresponding to the second to last row of the table. Dually, we define a maxterm as a sum term that includes the literals corresponding to all the variables of the function and for which the function evaluates to 0. Here, in contrast to minterms, each variable appears in the sum in its positive form x, if it has the value 0 in the input configuration of the truth table, and in its complemented form not x, if it has the value 1. Let me show you two examples using the same truth table as before. The maxterm a or b or c corresponds to the first row of the table. The maxterm a or not b or not c corresponds to the fourth row. Starting from these definitions, we can define the first canonical form as an expression that represents a given Boolean function, obtained as the sum of its minterms. Let us clarify this concept with an example. A truth table can be decomposed into a number of subtables equal to the number of ones in the function. Each of these subtables contains only one of these ones. You will agree that the original function is the sum of these new truth tables, since the function takes the value 1 in any of the alternative subcases we have generated. From each subtable, we can derive the corresponding minterm associated with the single one it contains. Finally, by summing all the minterms, we obtain the expression in the first canonical form. Thus, the first canonical form provides an initial answer to our question regarding the method to determine an expression that realizes a given Boolean function. Here is a more complex example. Without decomposing the truth table into multiple subtables, we identify all the entries where the function takes the value 1. For each of these, we determine the corresponding minterm and we express the final result as the sum of these minterms. Dually, the second canonical form is an expression defined starting from the function as the product of its maxterms. Let us revisit the same example and decompose the truth table, but this time based on the zeros of the function. Each subtable contains only one zero, and the overall function is defined as the product of these subtables. For each subtable, we can define the corresponding maxterm associated with the single zero it contains. Finally, we calculate the final expression as the product of the maxterms found. Let us revisit the second example from before. Without decomposing the truth table into multiple subtables, we identify all the entries where the function takes the value 0. For each of these, we determine the corresponding max term, and we express the final result as the product of these max terms. We have introduced the canonical forms in an intuitive way. Let us now proceed to their formal definition. As shown in this slide, the first canonical form of a function with n variables is the sum 2 to the power of n terms, obtained as follows. The first term is obtained by multiplying the product term formed by all the variables of the function taken in their negated form by the value of the function for the input combination consisting of all zeros. The second term is obtained by multiplying the product term formed by all the variables of the function taken in their negated form, except for the last one, which is taken in its positive form, and the value of the function for the input combination consisting of all zeros, except for the last one, for which the value 1 is specified. Then we proceed in this way, forming all the possible 2 to the power of n product terms, in which all the variables of the function appear either in their positive or negated form, multiplied by the corresponding value of the function. As can be observed, for all cases where the function evaluates to 0, the corresponding product term will vanish, resulting in 0. In conclusion, the resulting expression is the sum of the minterms. Duly, we can define the second canonical form. For brevity, we will not go into the details of the formulation, as it is the same of the previous one. The formulation of the canonical forms discussed here derives from the iterative application of a specific theorem, that is the Shannon's expansion theorem. This theorem states that a function f with n variables from x1 to xn can be rewritten with respect to x1 as not x1 and f, where x1 is always 0, plus x1 and f, where x1 is always 1. This rewriting, shown here for x1, can be applied to any variable xi of the function. As an example, we can rewrite a function f of a, b, c as not a and f, where a is always 0, or a and f, where a is always 1. Shannon's expansion theorem, now shown for sum of products forms, can also be duly applied for product of sums forms. The function f can be rewritten with respect to x1 in terms of not x1 or f, where x1 is always 1, multiplied by x1 or f, where x1 is always 0. Let us show an example. We want to calculate the first canonical form of this function, starting from the definition obtained by iteratively applying Shannon's expansion theorem to all the variables. We take the definition shown in the previous slides. Next, we substitute each f with the corresponding value from the truth table of the considered function, and we eliminate all the terms multiplied by 0. In this way, we obtain the first canonical form. Dually, here is the derivation of the second canonical form for the same function, starting from the formulation provided by the theorem. We take the definition shown in the previous slides. Next, we substitute each f with the corresponding value from the truth table of the considered function, and we eliminate all the terms added with the constant 1, thus obtaining the second canonical form. Shannon's expansion theorem can also be applied directly to Boolean expressions. Let us take an example. We want to expand the expression a and b, or not b, or not a and b, and not c, with respect to a. We obtain a and f of 1 b c, or not a and f of 0 b c, where f of 1 b c is equal to b or not b, while f of 0 b c is equal to not b or b and not c. At this point, we apply the distributive property to obtain the expression in the sum of products form. If necessary, in the obtained sum of products expression, we can apply the idempotence property to eliminate any product terms generated multiple times. Let us go into detail on how we derive the expressions f of 1 b c and f of 0 b c. In the first case, we replace a with 1 in the expression, while in the second case, we replace a with 0. Then we simplify both expressions with respect to the neutral element and absorbing element. For example, in the first case, 1 and b simplifies to b, while not 1 and b, not c, is simplifies to 0 and b and not c, which equals 0 and therefore disappears. Finally, the iterative expansion of an expression with respect to all the variables leads to the canonical form. Let us take an example considering the expansion with respect to the sum of products. We first expand with respect to A, then with respect to B, then with respect to C, and finally we apply the distributive property, thus obtaining the first canonical form. Consequently, we can then derive the truth table of the function.